Okay, so now I'm gonna show you some of the, kind of the actual results. What does this actually look like? So let me pull up this other set of slides here. Okay, so how's that? Oh, that's visible, I think. All right, so here is the E infinity. So I did this in a range. This is the E infinity page of the Chow degree 1 spectral sequence. So you count not just for the D1s that we talked about in terms of HI multiplications, but the higher differentials in terms of the MAPC products, then this is the stuff that's left. Okay, so this chart is, again, I'm using kind of classical degrees so that these vertical towers, these H naught, things that look like H naught towers here are really referring to H1 towers in semotypic X, and the degrees have to be all shifted out. These lines of slope 1 really represent H2 multiplications and so forth. Okay. On the other hand, the labels are like the actual names of the elements. So when I write putting C0 here, looks like it's in the 3 stem, but when you double the degrees, it ends up in the 8 stem, which is where you expect C0 to be. E0 is in like the 7 stem here, but when you double the degrees, it ends up in the 17 stem where it belongs and so forth. So those labels are the familiar elements. And then I did a little bit of color coding here to kind of tell you, see, this is telling you about the Adams E2 page, right? We're computing Chow degree 1 in the Adams E2 page. So these are all E2 page elements. But I was curious, well, what does that tell me about homotopy? You should always be kind of in the back of your mind. You should always be asking, well, what does it tell you about homotopy? And so there are 3 things that could happen. One thing, which is the black stuff, the black elements are just like things that survive to E infinity, and they're in semotypic homotopy. So that the black elements are telling you about homotopy. Then the blue elements are the ones that support Adams differentials. When I say do not support, I'm not talking about this spectral sequence. I'm talking about the succeeding spectral sequence, the Adams spectral sequence. These blue elements, like E0, doesn't survive the Adams spectral sequence. H0, H4 does not survive the Adams spectral sequence. So those blue elements are in E2, but they disappear. They go away. They're not really saying anything about homotopy. Well, that's not true because the Adams differentials, in subtle ways, the Adams differentials do tell you about homotopy, but I mean, it's not directly telling you about homotopy. Okay, and then the third thing that could happen is that these elements could be hit by an Adams differential, and so they could be 0 in homotopy. And that's the ones that I colored in green were that, just to kind of give you a sense for how this all fits together and what it all means. Okay, so let's look at this picture. I don't know. I guess let me try. I know it's kind of small, but I want to kind of talk a little bit qualitatively here. Okay, so you can see some structure here. So this is going out to the 30 stem, but remember when you double it, that takes really out to something around 60. You can see some structure here. There's some sort of repeating patterns up here along the top, although, there's some towers that just end, some of the hooks, some of these parallelograms, but it looks like something that might be predictable, and you can, maybe get some more data and kind of predict what's happening along the top. And then it looks like the usual story where something predictable happens along the top, and then something with a kind of a lower slope. There's some noisy stuff along the bottom that you don't really expect to understand very completely. That's at least what this picture so far shows you.
I asked what's happening with the C naught, H naught tower, H1 tower, really?
Yeah.
Here. Is that motivically non-zero, but classically?
So classically, it's
You just have
zero.
H1.
Well, you have H1, right?
That's
Exactly,
it.
and then and
So
then
they're not. The color coding doesn't tell us about.
it's not
this.
classical. It's semotypic. So semotypically, there's a whole
Right.
infinite eta tower there.
And the other thing is the towers with the hooks versus the towers without the hooks. Notice, well, there's a missing tower, but it's basically looks just like KO of RP infinity. The hooks are every other one.
It looks like it does.
Filtrations is pretty much right.
It does look like. I mean, it's dualized or something.
Well,
Right.
the KO, it depends on whether it's KO star of RP.
Oh, I see.
Or
Yeah. Right.
KO upper or lower
Yes,
star.
it does. It
And
does
the
look like
lower
that.
stuff looks a lot like what you see in TMF.
I think that's a little bit of an artifact of the fact that I just drew the H1 and the H0, H1 and H2 extensions. And so there's only so many different ways
Low
that those.
degrees, actually, that's where all the torsion is.
Yeah, right. So Yeah, and the thing to remember that these lines of slope 1/3 are really H3 multiplications, so there's something not quite lining up with TMS. Yeah, but okay, so, already you see, this is just some of the semotypic X chart, the semotypic E2 page. But there's kind of a high frequency of particularly interesting, particularly delicate elements in this picture. That's one of the things, if you know what you're looking at, which, I do, right? But it's sort of, so here's one example. So here's this element that I'm calling P. That little p, that's lowercase p. That's an element that ends up landing in the 33 stem. When you double the degrees, that's in the 33 stem. That's interesting because it's the target of a hidden new extension on theta 4. Okay, so that guy, that element little p, is related to the kind of the sort of pathological is maybe a little strong, but kind of like the complicated behavior of the theta ends. If you're studying the theta ends as a family, this is the first kind of, this is sort of a first thing we're saying, oh, it's going to get complicated, is sort of what that's saying. Okay, so little p is in there. There's another element here, capital D1. And then when you double the degrees, that ends up in the 52 stem. And that's a particularly interesting element because that element supports a D2 difference blue. It supports an Adams D2 differential, but the proof of that at D2 differential is particularly subtle. Okay, so it's like a difficult element to handle. It turns out that getting the Adams differential on that was in some ways it's hard relative to a lot of other things. Okay, so that's another thing that shows up. Another element that's coming in here is this capital D3. Okay, that capital D3, that's the reason that stable stems, the book Stable Stems, ends at the 59 stem. Okay, that element's the reason. Like, you can't figure out, using the methods of that book, you can't figure out what happens to capital D3. Does it support a differential or does it not support a differential? You don't know. Now, there are other methods came later that were more powerful that resolved that, and that's what it allowed us. But that was the thing that was the element that was for a few years, that was the limit of our knowledge. Okay, and it's showing up here in child degree 1. So, I don't know what that means necessarily, except that all of this, that we're getting at sort of interesting stuff. Okay, so then, let's take a look at the further. So this goes out to the 30 stem, and then I made another chart that goes out further. Okay, and let me say that this chart is reverse engineered. I didn't actually carry out the spectral sequence to get this. I took the computer data on what we already know about child degree 1, and I put it into this chart to kind of reconstruct the infinity page. Okay, I did it through the 30 directly, but this is kind of reverse engineered. Just want to point that out. Okay, so there's D3 again, just to kind of orient you. There's a little bit of overlap with the previous chart. So this pattern, along the top is sort of continuing, and it actually is pretty regular. These guys are kind of exceptional, and they're spaced out exponentially. And then it's just kind of alternating between lines and hooks, which is like a KO type thing for sure. Okay, but there's something down along the bottom. There's actually something qualitatively different that happens here that you didn't expect from or at least I didn't expect from the previous slide. I expected that noise along the bottom would have sort of like a lower slope, but that's actually not what happens. Here's this element, capital H1. And this element, capital H1, is actually G periodic. There's this line of slope 1/2, and these elements, there's infinite many elements that are lying along that line. That was not what I expected to see. Okay, turns out what's happened. In other words, the gap between this predictable stuff at the top and this noisy stuff down here doesn't grow. It's actually staying like a constant width. This is a line of slope 1/2. This is also a line of slope 1/2. And that's what's happening. Most of this stuff, in those terms, most of this stuff is kind of predictable from in a bigger perspective. And then there's still noise, and then there's still lots of noisy stuff down. So there's definitely more that could be proved about this. I don't know exactly what the statements are, but there's a lot of interesting structure here. And again, let me say that this was reverse engineered. I didn't actually do it, although you could. I just, haven't taken the time to do it. And there's a little bit more. Okay, so this is 56, so this is somewhere around 6, this is around 64. And these pink dots, just to kind of give you a reference, those pink dots are things that sit in the 126 stem. Okay, just to give you a kind of a sense of how far out are we with this, you know, that's not the 126 stem, that's just the elements of child degree 1 in the E2 page in the 126 stem are these pink highlights, just to kind of give you a flavor of, you know, how far out we are. Okay, and then it just trickles out because the computer data runs out, and so that's just as far as the chart goes. Okay, that's as far as this chart goes anyway. Okay, so what do I have? All right, before we do that, let me switch the view here. And I'll briefly show you a chart that Joey made this week. So this is, I'll zoom in a second here, but this is a picture, this is a chart. There's the 0 stem on the left side. The 256 stem is on the right side, just to give you a sense of the magnitude. This is a picture of the co-kernel of H0. Okay, so this is the E2 page of this child degree 1 spectral sequence. Well, the 0th filtration of the E2 page. Okay, so you take classical X and you just take the co-kernel of H0 in the naive ring theory sense, nothing to do with S mod 2. It's just you kill off the H0 multiples, and this is the picture that you get, just to give you kind of a sense of this. And this was, you know, this was a straightforward, easy, I mean, it was minuscule amount of computer time, right? Because we already have all the multiplicative data, it just had to run through and kind of tabulate it and make the picture, okay? And Joey also made pictures for the other layers of the spectral sequence. So, you know, there's a picture for kernel of H0 module the image of H1, and the kernel of H1 module the image of H2. We can look at it if you want, but you know, it's just some complicated thing. I said I was going to zoom in, but I mean, maybe I won't really zoom in. All you're just going to see are a bunch of dots and lines that still don't really mean anything. But you know, and there's obviously lots of regular patterns, and there's you know, some line of slope, whatever it is. Above this looks very predictable. Below this looks very noisy. You know, it's some big monstrous thing. But this is 256. So when you double that, that's when I say, you know, compute. This spectral sequence can be computed to 512 step. That's what I'm talking about. Now, the computer did this. That's great, but it's only the E2 page. We'd have to teach the computer how to compute the nasty products that we need if we wanted to compute the higher pages. Okay, which I think can be done. But it hasn't been done. And so, you know, so this is pretty far pre-infinite, but just to, you know, show you what's going on. Okay, so there's that. Yeah. So let's just go way out to the lower right corner. And you can see some of these, you know, some of these groups have very large rank. Tons and tons of elements there that are not H0 multiples. So big, you know, but we'd expect. That's why we use the computer to do this nowadays rather than do it by hand. Okay. Alrighty. Back. Okay, great. All right. So a couple of other things that we did along these lines. Well, one should look at the cohomology of A of 2. Just to, you know, so now I'm talking about the atoms E2, the motivic atoms E2 page for MMF, the sort of the motivic analog of the atoms for TMF. Okay, and looking in child degree 1, and this turns out to be exactly what you see. Okay, so first of all, it's pretty understandable. If you're familiar with the classical story, you might be a little puzzled by some of these things, like I've got the element C naught times G. You might think that C naught times G is 0, because classically it is 0, but motivically it's not 0, it's just tau torsion, okay? And it's in child degree 1. And of course, what you see here is KO, right? This very clearly looks like KO. But again, remember that really it has to be doubled, and so it's like a double copy of KO. Okay, clearly there's some structure there, although it's truncated in a funny way, right? It's sort of got this, it's got this missing column, but that's the sort of phenomenon you often see with those kinds of observations. Okay, well, that's the infinity page, but you could write down the whole spectral sequence and it's not that bad. You could do it in kind of closed form and it was sort of too easy, right? This is not very dense and this is all kind of worked out too nicely. So, normally you do the cohomology of A2 because it's just hard enough. It's hard enough that you have to work to understand it, but it's not too hard and you actually can understand it. This didn't have to work hard enough. This is in terms of difficulty, because of the doubling, this is more at the level of A of 1 in complexity rather than A of 2. So that tells you, well, okay, if you want a more challenging exercise, then you should study the cohomology of A of 3. Okay, so there is a motivic A of 3. It has X groups. It's not the E2 page of an atom spectral sequence, but it's an algebraic thing that you could do. You could compute the cohomology of motivic A of 3, and you could look in Chow degree 1 and look for elements. I mean, it's not a question that anyone's asking. And if you would ask me this question 6 months ago, I would have said, oh, that's like way too hard. Like nobody knows how to compute anything about A of 3. You're going to compute all the elements in Chow degree 1 for A of 3. Out of the question, not like, but nobody asked me that because nobody cares about, including me. I don't particularly care about Chow degree 1 elements in the cohomology of A of 3, except like, turns out, like, you know, like I said, I think, what did I say last time, right? That it's like a really clean answer to a really hard problem that no one was asking, right? And so that's what happens here. Okay, so here's what happens. So you just do it. Okay.
No, I did post A of 3 outside my door.
Yeah, fine.
10 years.
Yeah, sure. Right. You can look at A of 3, you know, but I mean, but nobody's like, for example, I don't think we've written down. Yeah, and it's in a range, like we haven't written down generators and relations for it. Not that I know of, right? I mean, you know, you could, it's finite, you know, I mean, finally generated, I mean, but finally presented, I mean, but you know, whatever. So anyway, so you can do it though. It turns out it's manageable. Okay, it's you know, it's the level of A of 2. If you can comfortable work on A of 2, then this is the picture that you get. Now remember that, you know, this is about A of 3, and remember you really have to double all the things again as always. Okay, but you see actually a really familiar pattern, and I color coded it a little bit to emphasize it. You see a stripe that looks like KO, and then another stripe that looks like KO, and then third stripe looks like KO, and a fourth stripe that looks like KO. But this whole picture, just like, you know, A of 2, everything is like, you know, each page is 48 periodic, or, you know, there's W2 or whatever. This is 104 periodic, because that's what happens when you double it correctly. And so then these 4 stripes of KO, then there's just 4 more, and then there's the delta 1 to the 4th multiples and so forth. So it's really, you know, there's really those stripes. And then there's some noisy stuff along the bottom. There's this guy here, the shutter black. Okay, it's a little different. So you see a whole bunch of stuff. This is all G periodic stuff. It looks like V1 to the 4th periodic in this picture, but when you double it, it's G periodic. So there's the blue and red stuff, it's all G periodic. And then there's this one family of things that in this chart looks G periodic, but that means it is really, when you double it, it's really G2 periodic, whatever that is, okay? So it's just, you know, there it is. It just works right out. It just all kind of falls right out. Okay, so it's a kind of a nice, clean answer to this problem. So yeah, the point. There's some question marks on here because some of these things I kind of know what their names are. I mean, some of these elements, I mean, they're in the cohomology of A of 3, but I don't have good reference points for them, and so I don't think they're not detecting things in the sphere, and so I just don't. We just don't have nomenclature for them. So it's not like I haven't figured it out. It's more like I just don't know what to call it because we just have to make up some names or something because they haven't really all studied before.
You have to wait until you know what you want to use it for to know what name.
Yes, exactly, right. So I mean, this is fine. This is cute, but this is a dead end. I mean, no, this isn't going to really be useful for anything except kind of like a proof of concept and so. Okay, and that's the end of that. Okay. You know, there's one other comment that I wanted to make since we decided that we're not in a rush. So I wanted to go back here. There's one other thing that I wanted to point out about this whole story. Perfect. There's this spectral sequence, there's this kind of this spectral sequence gadget that sort of kind of has this really kind of slick definition in terms of the HIs. So you could dualize this picture. You could draw these HI multiplications going the other way and sort of define D1s, okay? And then you could write down the brackets in the other order. So rather than it being H1 comma H2 comma X, it would be like, you know, H2 comma H1 comma X and so forth. You can write, D2s going the other way. You could build an object that looks like a dual version of this spectral sequence. It can be done. What I'm not doing, but it's not actually a spectral sequence, or at least not that I know of. I'm not starting with something and then filtering it and then getting the induced spectral sequence. I'm just saying, hey, here are some functions that behave like the differentials in a spectral sequence. Okay, but I don't know that it comes from a filtration. So it's sort of like there's a spectral sequence without knowing what it converges to. And I did it for A of 3, the dual one for A of 3 also, just because I could. And it came out to be a different, similar answer to the one, but a little different. Anyway, so I'm wondering, like, what this dual spectral sequence, like, it must be a spectral sequence. I mean, it fits together too nicely but what is it computing? I the foggiest idea of what that would mean, but that's sort of just a curious little spin off of this. Again, another sort of question that no one's really asking, but I wonder what that's related to. Okay, so that's the end of my first talk. I'm right on time. It's 2:30, so we're right on time to kind of fill up three hours. So now I'm going to start what was originally going to be the second talk.
Can I ask something here?
Yeah.
What's the, do you know off the top of your head I could probably just check, but, like, what's the chow degree of the last remaining guy?
So the Cavere elements all have chow degree 0. The problem, and we're going to talk about this a little more here later, is that things in chow, so the Adams differentials increase the chow degree. So something in chow degree 0 can support a lot of differentials. Okay, but because the Adams differentials increase the chow degree, things in chow degree 0 cannot be hit by differentials. Okay, so if we were worried about whether or not the theta n's were hit by any differentials, we would immediately know, no, they cannot be hit by differentials, but that's not the thing we're asking. We're asking whether it can support differentials. And so there does not seem to be anything particularly meaningful to address there with chow degree. Okay. All right, so I know it's sort of the middle of the talk and it's a little weird to kind of pause and like introduce my co-authors on this project. And I also wanted to mention some of the stuff that I'm not talking about is touching on some work that Constantine Emming has been doing lately. Okay, so and then I'm going to give some background motivation and kind of, give an introduction to the talk in the middle of the hour, but here it is. Okay, so study pi, let's talk about pi star of TMF for a minute. Okay, in pi star TMF, there are some elements, and they're in the Bruder-Rognes book, they're called nu sub k's. Okay, and they belong. They're sort of a regular family. They're in the 24K plus 3 stem, and they're detected by. And I put these squiggles in here because you have to be. They're sort of behaves a little different. And depending on K, the exact element is a little different. But in any case, they're all related to what Adams-Novikov people would call delta to the K, H2, and what Adams people might call V2 to the 4K, H2. Okay, so they're kind of very clearly like V2 period. There's a V2 periodic structure there, and then and anyway, and one of the things that makes these nu sub k's interesting, not the only thing, but one of the things that make them interesting is that they're not in the image of pi star of the sphere. Okay, so the unit map from S to TMF, people talk about the hooray, it's the image of that map, and it's was a big long-term project to compute it, which is now done. And these elements are not in the image of the sphere. Okay, so one of the things that means is that gives them more sort of freedom to behave weirdly, right? If they're in the image of the sphere, then the way they behave is controlled by the sphere. But if they're not in the image of the sphere, they can do all kinds of crazy things and still be consistent with the structure from the sphere that we know about. Okay, so Bruder-Rognes, amongst many other things, they calculated the products between computing the entire product structure for the homotopy of TMF. Okay, and they got nu 4 times nu 6, so nu 4 is in the 99 stem, and nu 6 is in the 147 stem, whatever, okay? And the product of them turns out to be nu times nu 2 is in the 51 stem, times delta to the 8th, the 192 stem. But there's this plus or minus, okay? And so their methods, they couldn't decide whether they knew it was non-zero, and they knew it was almost what it was, but there's this one little bit of information. They weren't sure whether it was plus that or minus that.
It generates the Z4, but.
Yeah, but you just don't know which generate, okay? And so then, together with my co-authors, I studied this question, and what we noticed was that you can actually work this out by looking not directly at nu 4 times nu 6, but you can multiply by G, or kappa bar if you prefer Greek letters. I prefer Latin letters, but if you prefer Greek letters, you can call it kappa bar times nu 4 times nu 6. Then you could study that in the homotopy of MMF, okay? And now MMF is important here because classically, kappa bar times nu 4 times nu 6 is 0. And so you think from that perspective, you just don't see anything. That doesn't detect anything. But notypically, this product is non-zero. It's tau coercion, but it's non-zero. And we were able to actually figure out what on the nose, not up to a minus sign, but actually on the node, we were able to figure out that product. And then once you know what it is after multiplication by G, then of course, you know what it is before multiplication by G, okay? And actually, if you look more carefully at what we did, what it's not, I mean, it is detected by the G times that, but it's actually detected by any power of G times nu 4 times nu 6. When you just look at the Adams Nova cost vector sequence, you kind of see that immediately. In other words, this nu 4 times nu 6, this difficult relation in the homotopy of TMF is actually seen in the G periodic version of MMF. Okay, so so the whole point of this slide is simply, well, it's right there at the bottom, right? Study G inverse MMF, G periodic MMF. There's something, right? There's at least one difficult piece of information that is in G inverse MMF. Now, ideally, you'd want to sort of study G inverse MMF first, and then use that to then deduce things about MMF. I'm not saying you can necessarily do that, but I am saying that it's carrying information that we care about. Okay, it's just there it is. It's nu 4 nu 6. It's carrying that information. Okay, so you might, this is I'm trying to motivate this idea that one should study G inverse of MMF. Okay, and let me point out kind of another thing about this G inverse of MMF. So there's sort of an analog of, there's actually kind of a thing that's already been studied, an analog of this. So KQ, little KQ, that's the name, sort of like that's motivic KO. Okay, that's the motivic version of little KO. Okay, if you invert eta or invert H1 on the motivic version of little KO, you get a thing that the algebraic geometers have a name for. Okay, they call it Witt-K theory. It's a thing. It's 4 periodic, and they studied it. And the theorem is that, there's a theorem that says that Witt-K theory is the previously known Witt-K theory is isomorphic to H inverse of little KQ. That's like, and that's the sort of thing like, it works over an arbitrary base field, motivic, not just C motivic homotopy theory, but an arbitrary base field. Okay, well, there's a sense in which, MMF is like the height 2 version of KQ, or TMF is the height 2 version of KO, and MMF is the height 2 version of KQ, and also G is like a height 2 version of H1 if you kind of think about it from the right perspective, okay? And so there really is a strong sense in which this really is a height 2 version of that, okay? So what I'm saying is that one should construct MMF, we only know that MMF exists over the complex numbers, but one could try to construct MMF over arbitrary fields. And I realized recently, when I say MMF, that's not really what I mean. What I really mean is construct EO2 over arbitrary fields. So I mean, just the fact two and work completed or whatever, like, it doesn't have to be an integral thing, but anyway, construct MMF or EO2 over an arbitrary field. Okay, and one should probably be studying G inverse MMF of a field. That's probably, that feels to me like that's an interesting invariant of a field that probably doesn't have, oh, maybe it does, but it, may or may not have kind of a, something that the number theorists or algebraic geometers were able to write down previously. Okay, just like, it's again, some sort of, higher version of this. All right, that's all very speculative. This is like grant proposal, blah, blah, blah stuff. There's not really, I'm just kind of, spewing out some, throwing out some ideas. Okay, so let's make it a little more concrete. All right, we studied there's this one interesting fact in the G periodic MMF. So what else could you learn about the homotopy of TMF from the G periodic calculation? Okay, so one thing is that if you look at the classical, here, I'll just scroll this still now. Stop there. Okay, so if you take the cohomology of A of 2, the classical cohomology of A of 2, okay, there's an element G, you can invert G, and what you get is something non-zero. Okay, that's actually not quite right, is it? It's not quite right. Let me just fix it here. Say it. Well, I don't quite know what to say. Let me do this. This is not the most efficient way to do it, but let me just throw in a G and a G inverse also. You don't really need 4 generators. You really only need 3 generators, and that's the right way to think about it in terms of 3 generators, but the notation is a little awkward. I don't want to get into that. So let me just I just want to point out that the G periodic E2 page, Adams E2 page is really easy to understand, okay? And it's not hard to do. This is just, you just look up what the generators and relations for the cohomology of A of 2 are, and you invert it, or you give it to Sage, and Sage does it for you, and this is what comes out, okay?
Well, there's actually a structural reason for this answer, why it has this curl dimension, and that is it's finite index in X over the subalgebra universe by square 0, 1, square 0, 2.
Yeah.
0, 0, 1, which is just polynomial ring. So
Yeah.
finite index.
Yeah.
Polynomial ring.
Right, so what Bob's saying is like, well, if you map to some other algebra related to A of 2, you'll see the polynomial ring right there, and it detects these elements, so that's,
Finite index.
yeah, right, finite index, yeah. Okay, so roughly speaking, what we're talking about here, what we're seeing here is what's, this sort of like this wedge, this classical wedge family. And it's really exactly the same as the wedge, modulo edge effects. The wedge is actually, some non-periodic thing, and so it can have the elements along the boundary can kind of behave a little differently. Things in the middle of the wedge are targets of differentials, but the things right along the edge, there's nothing below to hit them, so there can be little edge effects. But basically, we're exactly talking about the wedge when we talk about the G periodic classical classical cohomology of A. Okay, now here's an interesting observation. Okay, there are a number of additive differentials that you have to compute in the atom frequencies for TMF, but I think of 2 of those differentials as being hard and the other differentials as being easier by comparison. I'm not saying they're easy, I'm saying they're easier by comparison. Okay, and the 2 hard differentials, there's an Adams D2 on W2, that's the element of the 48 stem, and there's an Adams D3 on W2 squared, that's the element of the 96 stem. Okay, so those are the 2 hard differentials. Both of those differentials are G periodic, turns out. Okay, so that leads to this question here. How much of the atom spectral sequence for TMF can be determined by the assumption that G inverse TMF is contractible? Okay, so I mean this. So in other words, this is sort of a fancy way of just saying this. Suppose I make this assumption that in the atom spectral sequence for TMF, some power of G is hit by an Abs differential. Okay, I'm not even saying which power. I'm not saying that G to the sixth is or G to the fifth is. I'm just saying some power of G could be G to the 120. Okay, some power of G is hit by an Abs differential. From that very weak assumption, what can you deduce? Okay, and it feels like there could be a lot that could be. It feels like these differentials might be deducible from that very weak hypothesis. Okay, so that's, that's the kind of game you can play here. Now, you might look at this and say, well, yeah, the sheeted nilpotence. Well, not so fast. Okay, it's related to the sheeted nilpotence, but you have to know that G is in the Hurevich image of the sphere, which it is in the Hurevich image of the sphere. We know that, but how do we know that? Well, you got to kind of unravel these things and kind of see where they lead. So you want to be, if you're going to do G, if you're going to study G periodicity, you're probably going to want to assume certain things about G to begin with, such as it's in the sphere, right? Okay, so fine. So if you assume that, so anyway, so fine. So G is nilpotent of the sphere, so therefore G is nilpotent of TMF, right? So that's kind of what we're saying there. So the idea is that this is it's pretty close to like a formal consequence of the sheeted nilpotence, and then see what differentials. Yeah.
Let me ask you something before you scroll down.
Yeah.
Just about what's on the top of the screen.
Yeah, you're kind of feeling.
Well, you're making a case that G inverse MMF should be some over a field analog of EO2, but EO2 is not contractible. How are you?
No.
Isn't that what you said about G inverse MMF? That
No.
EO2?
I think of EO2 as just like the two primary version of MMF. Is that right?
It's reasonable, sure.
Okay,
Yeah.
all right.
I mean, EO2, it's K2 local TMF.
So maybe that's not where I want.
Quite a bit to it.
Maybe that's not really what I want. Let me just, let me retract whatever it is that I said about every sentence that I spoke today about EO2. Let me just retract every single one of those sentences.
Those were really good
Okay.
sentences. K2 local TMF conjecturally is the ring of Cat's p-atom modular forms.
Yeah, but that's somebody else's conjecture. I don't know what any of those words mean. So I'm personally retracting all that. I don't know
I mean, it
anything.
makes sense over different fields. So what you were saying about EO2 actually was pretty compelling.
Well, okay, fine, but like I was lucky, right? I just stumbled into that. This is really what I'm thinking. There's a strong analogy between this, which has a name, it's interesting enough to have a name, so I guess that means it's interesting. And this, it's just sort of the obvious analog. You just kind of raise the hands. Okay. So that's an invariant of a field. G inverse MMF of a field K is something that my instinct tells me is of interest algebraically, I guess. I mean, I can't define it because I can't construct MMF over, an arbitrary field. But I mean, it can be done. I just don't know. I'm confident that it can be done. I just don't know how. We don't have it. Okay. All right. I agree that, like, in some sense, that this is like the most. I don't know. This is kind of like the most interesting thing that I'm going to say in all these talks. I think is raising this question. That's my personal feeling. But I'm also in the sense of farming it out to other people, and I can't do that. I don't have the algebraic geometry or number theory skills to do that. But okay. All right. So this is all the introduction, like why we're going to study G periodicity. Okay. So now let's actually do some. So let's get into some details. Okay. So first of all, let's talk about classical periodicity operators. Okay. So there's this operator V1 to the fourth. That's an operator. So it's an operator on the classical stable homotopy groups. That's what I've got here. Okay. And what does it do? It takes an element X to the total bracket, X comma 16 comma sigma. If I write it with the Latin letters, but that's what I'm talking about. Things, talking about homotopy. Okay, and it's not really a function because it's not defined. It's only defined on the 16 torsion. That's only defined modulo the indeterminacy and blah blah blah. Yes, that it is all those things. Okay, but that's roughly speaking, that's what it is. It's this operator. Okay, and then you could. I mean, there's various ways in which you could try to generalize this useful structure. And one of the ways that you could do it is you could look at what I would call W1 to the fourth. Okay, so W1 to the fourth is again, is an operator, and it'll take X to some total bracket. And the most obvious thing to do, given the previous formula, is to write down X H1 to the fourth comma H4. Okay, and that's applying square knot. I'm applying square knot to H naught to the fourth and square knot to H3, and that's kind of where this is coming from. That's the idea. Okay, but I didn't write that because H4 doesn't survive, and so that doesn't make sense in homotopy. But I could put one of the H1s over there, and now H1 to H4 does survive, and so that does make sense. Okay, and that's fine. You can define that. You can define that total bracket, and that's an operator in homotopy. Turns out it's not really that interesting because it's just multiplication by kappa bar. And I'm writing these things in terms of Latin letters, and once in a while when I remember, I'm going to emphasize that, I mean, I really mean in homotopy, and so these kinds of multiplications could possibly be hidden in the algebra. Okay, but anyway, it's just multiplication by G or kappa bar by 20. Okay, that's all this operator is. We kind of already knew it. We had a simpler name for it. I guess is what I'm saying. It kind of collapses. It's not really a total bracket. It's really just a primary. Okay, and since it's a primary product, and since because of initiated nilpotence, we know that some power of kappa bar is 0 in the homotopy of the sphere, and so therefore, if you look at the W1 periodic homotopy groups, you have to get 0. Okay, just by issue. This is not 0, right? If you invert V1, it's not 0. That's V1 periodic homotopy, because this is not multiplication by an n, but this one is multiplication by n. Okay, so that sort of sucks, and you might give up at this point, and that's sort of a reasonable. It would be reasonable to sort of give up and say, well, there's nothing interesting here. Okay, but we don't do that. Instead, let's look at the motivic version of these things. Okay, so now I've changed the CLs into Cs because now I'm talking about C motivic homotopy. Okay, so you can define a V1 to the fourth the same way. That makes perfectly good sense. Okay, and you can define a W1 to the fourth the same way. And again, it's H1 cubed with H1 H4 to make sure that that they're permanent cycles. Okay, and then that's my definition of X times G. When I write for the rest of this talk, when I write times G, what I mean is this operator. Okay, I don't know why I'm putting it on the right. I should probably just put it on the left, like any normal person where it's a function. It's like P of X, right? We write PX when we mean that operator, apply capital P. It's like a function notation. And so I should have written G of X. I don't know. I don't know why.
It's good for people to deal with right modules every once in a
Well, fine, okay, yeah, but right. All right. So now there's a big difference here. Like you might say, well, this is the same thing I just wrote down before, that this operator was multiplication by something. But be careful. See, G itself does not survive. Okay, it's tau G that survives in the Adams E2 page. Tau G detects kappa bar, but G doesn't survive. So it's not just, so this operator is not just multiplication by an element. It really is like a secondary operator that you have to use the total bracket. Okay, and the consequence is that this can be non-zero, although I guess this argument doesn't prove that it's non-zero, but it's possible it's non-zero, and it turns out that it is non-zero. Okay, this W1 periodic C-motivic sphere is non-zero. Okay, and so you should probably study it. If it's non-zero, then we probably want to study it just because it's there, or because it might tell you about the C-motivic sphere, or who knows what. Okay, all right. So one thing that just to kind of get your hands on this thing and just to understand what it's telling you is, let's look at the Hurewicz map from the homotopy of the sphere, the homotopy of MMF. Okay, so X dot G goes to X dot G, which maybe looks really boring, but there's actually some content here, because on the left side, I mean this total bracket involving, this whole eta 4 and eta cubed and stuff. There's a total bracket here, and over here in MMF, G really is an element, and so it's just a primary product. Okay, so it's actually saying, I'm saying that this total bracket under the Hurewicz maps takes total brackets of this form to primary products of that.
and that's just how you do that.
Just like with atom periodicity, exactly. And that kind of explains why I take this, the reason I say this proposition is I'm trying to motivate this notation. Why am I calling this times G? What does this have to do with anything with G? Well, that has a lot to do with G. Okay, over TMF, it's just literally multiplication by, or over MMF, it's multiplication by G. So we'll use that same notation for the sphere, although we don't, again, we mean the function, G applied to the element X. Okay. All right, so, couple of notes here. What's the point of this first remark? I wrote this 2 weeks ago, and I'm sure I had a really, really brilliant reason to say this, but maybe the point is that a lot of these things that I'm going to talk today about semotypic homotopy can be rephrased in terms of the Adams-Novikov E2 page, okay? And so when I'm talking about this W1 periodic homotopy, that can be rephrased, or maybe it implies or something is closely related to this idea that the G periodic Adams-Novikov E2 page is non-zero. But you have to be careful about what you mean by G periodic. Okay, so what I mean by G periodic here is this particular Massey product. Now I'm in an Adams-Novikov E2 page, so I'm saying Massey product instead of total bracket. And beta of 16 just means like it's some beta family element. I don't know what its name is. I don't understand that notation. So it's in the 16 stem. So it just, for those who know what beta is, I'm just telling you, it's the appropriate beta element that happens to be in the 16 stem. What it is in terms of slashes and that, I don't know, but it's that, okay? So you do that, and that's right. Not multiplication by G, by the beta element in the 20 stem that detects kappa bar. It's not doing that. That's nilpotent, the Adams-Novikov E2 page. I think even its square, I think is zero. That beta of 20 squared is zero. So I don't want that. That would be zero. If I invert that element, I'll get zero. But if I invert this operator, I get something non-zero. Okay. All right. And then the other comment is that, yeah, I wrote down W1 to the fourth in terms of, H1 cubed and H1, H4, but you can do higher analog. You can define a W1 to the 8th operator involving H1 to the 7th and H1 to H5, or W1 to 16th involving H1 to 15th and H1 to H6, and so forth. And higher ones, and so we're talking about these Mahal eta J's are showing up here. Okay. And the point is that, see here, this is only defined for classes that are killed by eta cubed. Okay, well, what if you have a class that's not killed by eta cubed? There are such things, typically there are such things that are not killed by eta cubed. Well, then you can do W1 to the 8th. And as long as it's killed by eta to the 7th, you can do W1 to the 8th. And as long as it's killed by eta to the 15th, you can do W1 to the 16th. So as long as it's eta power torsion for some power of eta, then some of these, at least these higher order operators apply. Okay, so that's the kind of structure that I want to study in semotypic homotopy. Okay, so I'm doing this is all got the feeling of like some W analog of V1 periodic homotopy, and that's absolutely the inspiration behind this. 100%. That's where I'm coming from in this. Well, you can study V1 periodic homotopy and you can resolve it. So what about this sort of this analog? Okay, can you say anything about this? Okay. All right. Well, let's look, just because it's a starting point, let's look at W1 periodicity in chow degree 0. And I think that everything that I'm going to say for the rest of this talk, I think is all in chow degree 0. Okay, so that's part of why I gave the previous talk, because I wanted to be able to have that language. So just study things, of the X groups in chow degree 0, which is isomorphic to classical X. And these are the same degrees, the same degree shifting that we've been talking about all along happening. Okay. And over here, there's the Adams operator, capital P, it's degree 8, 4. I didn't write that down, 8, 4. And then under this isomorphism, this P operator corresponds precisely to this G operator. Okay, so that's good. That's something that we can take advantage of. If there's things we know about P in classical X, we can translate that over into properties of G over here in this chow degree 0. Okay, and so then you could then V1 periodic elements over, in the classical story are gonna correspond to W1 periodic elements over on the right side, and so I made a little table here. Okay, a little picture. Okay, so, this is the, this is, this is the motif at the top of the Adams chart. There's this check mark, and then there's a tower and this little thing, and then this thing repeats every 8, 4. This pattern repeats all the way across the top of the Adams chart. The lengths of these towers are different. And there's like a color that's not coming through here. This is supposed to be a different color than those, but anyway. Okay, so there's these p to the k h1, p to the k h1 squared, p to the k h1 cubed. That's these 3 elements, and they correspond when you double them, h2 g to the k, h2 squared, g to the k, h2 cubed, g to the k. And these were studied a few years ago by Michael Andrews. Okay, so Andrews already proved that these guys are like permanent non-zero cycles, and they're sort of exotic elements. They're W1 periodic family in motivic homotopy. Okay, and p k to the k c0, that's and p to the k h1 c0. The next two, these two are these 2 guys over here, and he studied those also. And this is their names when you double them. Okay, and then there was one other element that he studied, which is the one at the top of these towers.
It's just a different color.
Do you see it?
I can tell. It's a slightly darker yellow. The one below it's a lighter yellow green.
Yeah, it looks on my screen, it looks like completely green here.
Yeah.
Let me. Now I'm going to be a perfectionist and change. There. Okay, now it looks good. Okay, so then the last element that Andrew studied was the element right at the top of the tower. He didn't study the thing, but just the element that's the cyclic group, but there's sort of a unique element that's of order 2. And he studied just that one element. Okay, and there's sort of an analog for it. Okay, so those guys, Andrew's already kind of, thought about those. All right, but then of course, as you see on the bottom of the slide, there are other V1 periodic elements. That's the pink ones, and oh, that one looks better. That one's maybe it's not next to the yellow. It looks more green. Okay, so there are some other V1 periodic elements. There's these 2 guys. Okay, that Andrews didn't touch. Okay, and we're going to figure out what happens to them. Okay, we're going to answer that. And then there are doubles. There's h3g to the k and h1 h3g to the k. Okay, so we're going to study those. And then there's these H0 towers in these stems that are 7 mod 8. That's this. Well, it used to be green, now it's orange, right? These guys, and they have varying lengths, and so this is the most interesting, most complicated part of V1, most number theoretic part of V1 periodic homotopy. So the orange stuff, that's the prize. This is all like the easy, picking off the easy stuff, right? Including the pink, right? That's the easy stuff. But then the orange, that's the interesting stuff, the most interesting stuff. So we're going to try to figure out what happens there. So then these H0 towers correspond to H1 towers. And, it's a little, because of the degree doubling, it's a little hard to kind of orient to be specific about where they are. And so there's this co-weight that actually ends up being useful. Okay, so you take the stem minus the weight, there's another degree. It's not the chow degree, it's just some other degree that we call co-weight. And the point is that the doubling takes these guys to and it's sort of a predictable co-weight. And so I can kind of refer to it. You're smiling because you do.
Well, it's terrific, right? I mean, Adam showed that the length of this the length of your orange tower is the 2 it's given by the 2-atom valuation of the Bernoulli number, right? And so this is classical, right? It's wonderful.
Yeah.
But you're telling us that you're getting a bunch of eta towers in the motivic stems, right? But their length is determined by something like that.
Something like that.
Yeah.
Yes, that's exactly what I'm saying. Yeah. Well, let's see. Let's see what the next slide says. But yeah, so we're at 3 o'clock around time, and so maybe this will be a good place to. This cliffhanger will be a good place to wrap this up.
Those Bernoulli numbers, you string them together into an L function, right? And like all the equivalent amount stuff, all this deep number theory shows up to specifies that L function give you the lengths of these towers. Now you're getting some kind of connection, presumably to L functions from the lengths of eta towers.
Well, it's a little different. Well, okay, the lengths of the towers are going to be a little different.
Yeah.
Okay, actually, they're going to be a lot different, and which in a way that I think is actually kind of intriguing.
Great.
Okay, so not a lot different in the sense of and like it breaks down, more like a lot different in the sense of like, oh, this is like a whole new world. Like it's like trans V1 periodic rather than, but anyway, but it's 3 o'clock, so, stop? Yes?
Yeah, makes sense.
I think we should probably just
Do you have
stop.
enough to fill next time?
Well, probably not to
With
fill
the-
next time, but I have plenty to say.
Okay.
I mean, it'll be enough for people to, I have enough to say that it'll be worth people coming in and sitting down and getting comfortable and listening to it, okay? So, right, including all these like nice pictures and stuff, right? But
Very good.
I gotta go recolor them though, all because, I gotta get rid of that green, yellow
Can
problem.
you give us a preview picture of where those
Yeah.
media towers, can we see some of them?
Well, I mean, well, what do you mean by see them? I mean,
Is there a place where we can see anything of the lengths of the first view of them?
yeah. Here. There. No, that's those are the links of the, no, that's not the right one. It's not the right sequence. This is the right sequence. Oh, yeah, sure. 1 second, okay. There. It's gonna come this, okay, that's the sequence.
Where?
In those numbers that are highlighted.
Oh.
Are those the
So-
exponents?
Instead of, you normally see like 3, 4, 3, 5, every other one is 3, right? Those are the stems that are 3 mod 8, like
You mean 2Q?
you actually.
When you say 3, you mean?
Well, I mean, the log of the order. I mean, I see
Yes.
3 dots and so I say 3, right?
Yeah.
But yeah, of course, yeah. So the 3s are replaced by 2s, okay? The 3, 4, I mean, these are a little different.
Yeah.
But so the next ones are replaced by, the 4s are replaced by 6s, right? And then there's 12s, and then there's, I don't know.
Yeah, you're supposed to think like 2, 4, 2, 8, 2, 4, 2, 16, this kind of congruence pattern.
Right, but it's not that.
It's not that, but it's close to that.
Well, it's close in a very qualitative sense, that we've talked about before, about like it's two-adically continuous. Like the values of these functions they only depend on the 2 divisibility.
Yeah.
So they're kind of, it's the every other and then every 4th and every 8th, that's what the colors are sort of showing. But the numbers that you get are different. And then there are other problems also that we're gonna have to talk about in more detail. So it's a little more complicated than that, but there's structure here and it's different structure. And I mean, I'm sort of taking the punchline, I'll say it anyway, there are a lot of places in stable homotopy theory where you see stuff that looks like the image of J. And when you see, and that's fine as far as it goes, but it's the same number theory every time. It's the same sequence, it's the same number theory. Okay. This is a situation where my experience, my instinct tells me that you're seeing a genuinely different pattern here. This is not just some like linear transformation of like the V1 periodic orders. It's not that. It's like it feels different in a way that's actually kind of rare in homotopy. It's kind of hard to stumble across some pattern other than V1 periodic homotopy. And that's kind of what this feels like. But there's a lot of bullshit in that too. I just,
Is this pattern up here 8 periodic? You got 8 patterns of 4.
it's
Is
so,
it gonna be 3, 2, 7, 2, 6, 2, 15, 2 after that again? With the 31, but then the question mark, who knows, and then 63 become a 127.
so it's, maybe it's easier to kind of see it like, it has periodicity in the same sense that this is the classical order image of J. In the same sense that this is periodic, right? It's the ruler pattern, right? I mean, so it gets longer and longer.
So you take this, we've got
Yeah.
8 groups of 4 here, so that same 8 groups of 4 will repeat.
Yeah.
Except the tail end will change.
Right. And then
That
you have a
would-
larger pattern
That
and then,
group, those
Yeah.
16 repeat.
yes,
Except the tail end. changes.
right, exactly, right. It's that same kind of like,
Right.
it's just, I mean, I really think of it like the visualization I like most is this one, like, because it looks literally, I call it the ruler pattern. It looks like the marks on a
Sure.
on a ruler, on an imperial,
Well,
not on a digital, not on a metric ruler, but on like an imperial ruler where, it looks like that literally. And so it's also kind of a fractal thing, right? Where each time, you kind of double it and then it's the same thing again, so there's various ways of saying. And then there's a number of theoretic ways of saying.
Two-adic valuation.
It's the two-adic valuation. This one is just the two-adic valuation. The other one that I'm telling you is it depends on it's a function of the two-adic valuation. Almost, but it's not actually the two-adic.
I would suspect it's the two-adic and the 24-adic valuation.
Well, it's certainly possible, yeah. It's certainly possible that it only depends. It only depends on it's possible that it depends on the primes 2 and 3. It's possible, although there's data that like raises question about whether
that would be
or not, but I don't know yet. I don't know.
Can I ask you something?
Yeah.
I also have, but first, when you talk about W1, are you talking about like the exotic symptomatic periodicity stuff? Are you talking about the and the?
No, I'm not talking about, I'm talking about, an exotic motivic periodicity.
Also, I want to say something about PO2. I think that Andrew maybe thought that Dan was talking about capital PO2, just like fixed points of Dan was talking about connective. Now the connective cover of this is just something whose cohomology is in mod AO2. And that's what he was that's what he was asking for.
So, look, I think that's correct. It is certainly the case that, like, to me, like, the only thing that I care about when something is called TMF or whatever, its cohomology is A mod AO2, or its atom spectral sequence is X over AO2. That's all I mean. Yeah, okay, and I was under the vague impression that this EO2 was like easier to construct. Little EO2 was easier to construct than integral TMF.
Yeah.
And I only care about the prime 2 anyway, so why not just go with the easier construction? That's what thank you for helping us clear up that discussion. Okay. Okay.